Hey guys, Miss McMahon here, and I wanted to spend some time today going over some of the common misconceptions that I see my students struggle with as we work through Unit Circle material. So I'm just going to work my way through a list I've created, and I hope you find this helpful. So the first thing that I see students sometimes struggle with, and I find it's really helpful to remind everyone, is that when you have a trig function like sine, cosine, or tangent, that first of all, those are the functions. Those are the functions similar to the square root function. The input of those functions, the input of a trig function is an angle. So we take angles and we plug them into sine, cosine, or tangent, or any trig function. And those angles may be measured in degrees or they may be measured in radians, but regardless of the unit of measurement, we take angles and input them into trig functions. And then the output that we get from those trig functions are ratios. They're a comparison of two triangle side lengths. They do have to be right triangle side lengths. We know that. But the ratio is how two sides of those right triangles divide by each other. So, hopefully that's a good place to come from, to remind yourself that we input an angle into a trig function and what we get out of it is a ratio comparing two sides of a right triangle. The next thing that I see my students struggle with, and I think a lot of people will relate, is knowing or checking which mode your calculator is in. So if I hit the mode button right here on a typical graphing calculator, I can see 3 rows down that I have the option between radians and degrees. So my calculator is currently in radian mode because that's the word that's highlighted. That's the unit of measurement that's highlighted. So if I hit clear and I go back to the screen, that means I can calculate the cosine of pi over 4, pi divided by 4, and get the correct answer. However, if I want to calculate that same angle for cosine in degree measurement, if I want to get the correct answer, I'm going to have to first go to mode. I'm going to have to go down 2 rows to the 3rd row. I'm going to have to go over to degree and hit enter, where degree is now highlighted. And then I can hit clear. I can evaluate the same angle, the cosine of 45 degrees, so it's the same angle as pi over 4 in a different unit of measurement, measured in degrees instead of radians, and I can get the same answer for that, for the evaluation of cosine at that angle. But I had to change modes before I was able to get the correct answer. If I were to type in the cosine of pi over 4 now that my calculator is still in degree mode, I will get a different and incorrect answer. Okay, so we want to make sure that if we're evaluating a trig function and we're working in radians, that our calculator's in radian mode so we can get the correct answer. And if we're working in degrees, that our calculator is in degree mode so that we can get the correct answer. So that's important. The next thing that I see a common mistake on with students in working with the unit circle is I see students place their reference triangles or reference angles in the wrong direction. I see students do something like this, where they put theta at the origin and they put their right angle on the y-axis to create their reference triangle. Now you will never have a reference triangle along the y-axis. And let me explain how I think about this. So first I'm going to draw in the correct reference triangles in all 4 quadrants. So we have the right angles along the x-axis, and we always have theta at the origin. Now, first of all, I sometimes think that this looks like a butterfly, that it looks like a butterfly's wings. So I hope you find that little trick helpful and use it as a memory trick in the future. But the reason that, another way that I think about this, and again, we always have, the unit circle always has that radius of 1. I think about this as the triangles represent how we get from the origin to the coordinate point where the angle intersects the unit circle. And we did that by traveling along the triangle legs. And so first we traveled along the positive x-axis, and then we traveled along the positive y-axis, and that got us to the coordinate point x, y. In quadrant 4, we traveled along the positive x-axis, then along the negative y-axis, and that got us to the coordinate point x, negative y. Over here in quadrant 2, we traveled along the negative x-axis, along the positive y-axis, and that got us to the coordinate point negative x, y. And down here in quadrant 3, we traveled along the negative x-axis, then we traveled along the negative y-axis, and that got us to the coordinate point negative x, negative y. First of all, this mode of travel on the coordinate grid, following these triangle legs, as first on the x-axis and then along the y-axis, is how you need to plot a coordinate point to begin with. Whenever we plot any coordinate point, points on the unit circle not excluded, we first plot the x coordinate, or we travel along the x-axis, and then we second go to the proper spot on the y coordinate, or travel along the y-axis to get to that coordinate point. And if you set your reference triangles up like this, with your right angle along the x-axis and theta at the origin, then you will do just that. You'll go from the origin, first along the x-axis, then along the y-axis, and get to your proper coordinate point, which is in alphabetical order. X first and then y. So maybe that helps with the next misconception that I want to talk about, which is where students get confused about what is positive and what is negative. And for x and y, that simply depends on, did you go along the positive x-axis or the negative x-axis? Did you go along the positive y-axis or the negative y-axis? And it's a little confusing because we're talking about sides of a triangle that now have positive and negative values depending on your direction. We're also talking about the radius of a circle, which in these cases corresponds to the hypotenuse of a triangle. And for these values, we are sort of sticking to the idea that it's a distance, and a distance can never be negative, even though we have kind of broken that rule for a distance like this, where we travel down the y-axis, and therefore that means that's where the y values get negative. So I realize it's a little confusing. We've got two sides of a triangle along the x and y axes that now can be negative, depending on which direction you go. And then we've got the radius or hypotenuse side that is always going to be positive. Sorry if that doesn't sit well with you. All right. The next thing that I also understand can be confusing is, say we're looking at the angle 3 pi over 4, which we got to 3 pi over 4 by starting at 0 radians and traveling this rotation and creating that angle where theta equals 3 pi over 4. The tricky part is that then we use a reference angle or a reference triangle that we set up over here to evaluate that angle with different trig functions. And that means we put theta here and we say, hey, that's pi over 4, because that's how much is left until we would get to 4 pi over 4, which reduces down to pi. Which again is confusing because you look at these two things and you say, hey, those aren't the same thing. But the tricky part is they get you the same values. So while we did travel from 0 radians along the green angle arrow to 3 pi over 4, we're then using the reference triangle that creates, which is a 45, 45, 90 reference triangle, because pi over 4 is equal to 45 degrees. We're using that reference triangle then to evaluate it. So we're always looking for the distance from that angle to the nearest x-axis, wherever that may be. So I understand that's a little tricky as well. And if you need to review reference angles or reference triangles, I strongly recommend that. Lastly, I wanted to address the misconception is once we get fluent with the unit circle, we start seeing problems that sound like this. It'll say evaluate the trig functions from the coordinate point maybe we'll say -5, -10. Well, I can plot that coordinate point. It's right here. And I can create a triangle with it. And I can put my right angle on the x-axis, and I can put theta at the origin. And I can say, you know, this is a distance of 5 or -5 if we consider the direction, and this is a distance of going down 10 along the y-axis. And we might want to say that the cosine of theta is the x value, and the sine of theta is the y value, and the tangent of theta is going to be the y divided by x value, or the sine divided by cosine. And you'd be correct on one of those out of 3. But here's the problem. These patterns, or at least sine and cosine, only work within the unit circle. And the problem we have right now is that we're way outside of the unit circle. If I were to draw the unit circle in on this diagram, it would be maybe about here. Maybe. Because if we go -5, we've way surpassed the unit circle radius of 1. Because we know the unit circle has a radius of 1. And so if we're way outside the unit circle radius, way outside the circumference, then our hypotenuse is no longer going to be 1. And that means we are going to divide by it to get the sine and cosine value. And the values of -5 and -10 are going to change because we're not dividing by 1. So while we could evaluate tangent by doing -10 divided by -5, we can say the tangent of theta is -10 divided by -5, which is +2. We cannot say that the cosine is simply -5 and that the sine is simply -10. We would have to use the Pythagorean theorem to solve for the c length here, our hypotenuse length. And we would have to actually do that division because, again, these patterns only work in the unit circle where you have the hypotenuse or radius of 1. And we need to ask ourselves, are we working within the unit circle, or are we outside of the unit circle where some of these patterns do not hold true? So I hope you found that helpful. I hope this helps you to get around some of these mistakes and not make them. I'm here to help, so let me know if there's anything else I can address. Thanks, guys. Have a good one.